My name is Tom Gransden and I'm a PhD student from the University of Leicester. My research area is interactive theorem proving. We live in a world where technology systems are everywhere. Many of these systems are business critical, but we also depend on them to be safe. Unfortunately, this year alone we have seen all of these compromised by software faults. Many people can be affected by a single error, so it is incredibly important that we can trust our IT systems. One way of overcoming these problems is to use an interactive theorem prover. This is a piece of software that a human interacts with to construct proofs. The process begins with the human providing a theorem statement that they wish to verify. The human then enters a sequence of commands that justify the original statement. After each command, the computer provides a response suggesting whether the reasoning is valid or not. This continues until the computer hopefully replies that the statement is true. It is possible to use a theorem prover to show that a program meets its specification. Although a promising technique, theorem proving is an expensive task due to the amount of human effort required. Finding a proof is like finding a way through a maze. There are typically many different paths to take, and sometimes you may get close to the end but have to start over. During a proof there are many commands to try, and they work with varying degrees of success. Finding one proof can be complex, but there could be many statements to prove. In a recent project to verify a code compiler, there were over 5,000 proofs to find. The overall effort took 4 years with a large team of experts. The computer can only solve a small proportion of proofs by itself, leaving a large workload for a human to complete. In my work, I use the Koch theorem prover. This is a tool that has been widely used in many industrial and mathematical proof developments. Although some simple automation is provided, the proof effort can still take many years. My work aims to address this important limitation. There are thousands of examples where an expert has provided the necessary sequence of Koch commands. It is not practical to look through all of this information manually, however machine learning allows computers to process and learn from large amounts of data. The approach that I have designed is called Sepia. Sepia processes the example proofs and tries to identify something useful from them. The output is a model called a state machine that suggests possible sequences of commands to try. These strategies can be used automatically during proof attempts. The computer can now complete many more proofs on its own as it has been guided by Sepia. I have already shown that a much larger proportion of proofs can be found automatically. This is a significant reduction in the amount of human effort required. In the future, I hope that Sepia will be used to produce more trusted software and also by mathematicians trying to find the next big breakthrough.